simple one before, method of joints, and now we'll look at a typical, much larger, more detailed truss analysis. Structure looks like this. So all the joints are labeled, spacing is 10 feet in both directions. Horizontal load applied at the top at joint C, and vertical loads of 10 kips, so that's 50 kips, 50,000 pounds. And at I, J, and K, I'm applying a force down 10 kips at each of these. We have 3 reactions for this truss, and what we want to do is solve for all the member forces. But first we'll solve for the reactions based on overall statics of the truss. And you can see we have summation of forces, and we won't solve for every bar force, we're going to get bored of it. But I want to show you how to solve various joints so you get an idea. We'll get just past halfway, and then it's the same process after a while, okay? So it won't take all the class to computers. Otherwise, it would take all the class time. So summation of forces in the X is 0. This is overall statics. We only have one horizontal force applied, that's the C. If we had another one, we would include that. And so we have reaction AN to the left, has to equal everything to the right. So even for a large structure like this, you can see the reaction just comes down to something as simple as that. Like I said, if we also had other horizontal forces applied, that would be included in this equation, right? If we happen to have, let's say, another 10 and D to the right, then this would have been 60 kilos. So now let's solve for, what's our question?
Yeah, what if there was a force applied to the left on top at the same time?
Then that would be included in this. So if you had, you mean a D? or a C.
Yeah, like if you've had like 10 kips per left.
Well, it'd be 50 equals 10 plus the reaction AX, so it'd be 40. It's just good. Or if you want to, set them all equal to 0, it'd be 50 minus 10 minus R sub AX equals 0. And you'd still get 40. And you don't have to draw it this way, but it's very clear the reaction is going to be this way. I could draw it this way. I would say, in that case, 50 plus R sub AX equals 0, and then 50 R sub AX equals minus 50, which means the opposite to the direction of 0, which would still be the same. Either way, you get the same. Okay, let's find solve for reaction of B. The way we do that is we're going to sum moments about A, right? So we have R sub B. Let's put summation of moments about A equals 0. And when you sum moments about A, you have the reaction in B multiplied by the whole length, right? So you're taking moments about an axis coming out of the page right here. And so, and the reason you're taking it there and not, let's say, at H is because if I sum moments about, let's say, H, an axis coming out of H, I would have to include R sub B multiplied by the distance to that location, but I'd also have to include the unknown R sub AY times that distance as part of the moment equation. I would have this 50 times this height, the R sub B times the distance here, and the R sub AY. So the reason I'm taking moments about this point is so I don't have to include that because it doesn't have a moment contribution. The other option would be we take moments about here, and then I wouldn't have to include R sub B in that equation, and then the only unknown would be R sub AY. I don't include R sub AX if I'm summing moments about here or there because it's going right through those 2 points, so there's no moment contribution. If I sum moments, let's say about D, I would have to include R sub AY multiplied by 20. I would have to include R sub AX, 10, and R sub B times the distance over to that horizontal, okay? Anyway, so that's why we're summing moments where we are. And it doesn't matter, I can sum moments about A, it would give me R sub B, or I can sum moments about B and then it would give me R sub A. But it's eliminating one of the unknowns. So I choose, in this case, to sum moments about this axis here. So my unknown is R sub B. What's the length? What's the total length? We're adding 10, 20, 30, 60, is that right? So that counterclockwise, and then you can see that's got to be equal based on overall status of the structure to the clockwise moments about this point. So let's start with the 50. It's 50. That's the force, and then the normal perpendicular distance of that force to the point we're taking the moment is 10. So here's the 50. This is the 10. That's clockwise, and you can see each of these 10 kips applies a clockwise movement, right, about A. If I was summing moments about B, all of those forces would be counterclockwise. Okay, so you have to think in terms of where are you summing the moments. What's clockwise, what's counterclockwise. So this is plus 10, that's 10 kips, multiplied by 20 feet to A, plus 10 times 30. Plus 10.
He's gone.
Then the only unknown then is R sub A. So 20 to here, 30 from here to here, and 40 from here to here. R sub B is 23.3 kips. Then the final thing, so we know R sub B, we still need R sub, let's put that, 23.3. And then we need to solve for R sub AY, and we use the third equation available to us from statics. So summation, of course, vertically has to be 0. So I have R sub AY plus 23.3. simple, so the horizontal force doesn't enter into this, we're just summing the vertical forces, so those two reactions up have to equal 10 plus 10 plus 10, which is 30. R sub AY is 6.7. So, now it's interesting, you can see, just looking at it now before we solve for the individual member forces, that the two forces up, 23.3 plus 6.7 is 30, and that balanced by the forces applied to the structure down, 30. Again, this horizontal force doesn't enter into that, because we're just looking at the vertical forces. Longitudinally, you can see this 50 is stopping the structure from rolling. There's 50 kips applied that way, and it's being held back with 50. If we did not apply this 50 kips, not only would that reaction go to 0, but these two vertical reactions would be equal, right? Because the 30 kips applied at the three joints is down, it is centered. And so you would have 15 and 15. It would still add up to the 30 kips, but the distribution of the vertical reactions would change. It's applying this lateral force causes this to increase from 15 to 23.3, and this to decrease from 15 to 6.7 because of the overturning moment from the low to high. It also causes this reaction. Is that clear? You have to imagine that's what's happening. And our statics bears that out. So trust your statics. Sometimes things look funny, but it turns out the statics is always right. Unless the structure's moving, actually going. Then it's dynamics, which we'll talk about a little later in this course. So we'll start with joint A. Do you see any zero force members before we start? Talked about that last. I actually don't see any. I mean, this would be a candidate. If we didn't have a force applied there, this would be a zero force member. This would be one of those rules. 3 members, 2 parallel, 2 in line, 1 off. But because we're applying a force here, that, remember, you can't have a force applied there. So this member will have a tension force of 10 kips go directly. And all the other ones, I don't see any zero force members. So we're going to start with joint A. There's the joint, just a little circle, and all forces and reactions that are there have to be included. So now we're going to do statics, instead of statics of the structure as a whole, we're going to do statics joint by joint, right? Which is a little different in the sense that we only have 2 equations available to us. Summation of forces in the X is 0 and summation of forces in the Y. There's no moment at the joint, so we're not summing moments, okay? We only sum moments to the structure as a whole. So there's our joint. We have 50 being pulled to the left. The reaction is pulling on the joint. And the reaction is also pushing up with 6.7 kips. We have an unknown force here, F of AH, that's the member force that we're trying to solve for. And we have F of AC. Now you don't have to draw them the directions I drew, and we could change the directions. As we'll see, there are probably a couple examples here where you get negatives, but I mean, for me, I can see that, and then this angle here is theta. In this case, because the dimensions are 10 by 10 everywhere, this is going to be 45, this theta is 45 degrees. So for this particular example, since theta is 45 degrees. Cosine of the angle, the sine of the angle happen to be the same as that cosine, at 45 degrees. But that doesn't mean you can switch the equations of cosine and sine still would be wrong, even though the numerical result would be right. So you still have to be careful. So in in this case, I drew this F of AC. Like I said, you could draw it the other way, you'll still get the correct result. But I drew it down as a compression force because I can see that the only vertical component is the 6.7 kips up. So this has to be down so that the vertical component of that force is going to be balanced at 6.7, okay? But like I said, if you draw it the other way and you sum the forces, you'll just get a negative, which means it's the opposite to the way you have to draw it. So you don't have to instinctively know which way these forces go when you draw each joint. You just draw something. But if you see which way it's going to go, it helps. In this case, since I know this is this way, now imagine I know this is going to be to the right because it's got to balance that 50 kips plus that horizontal component like that. Okay? That's why I drew it that way. But again, you could draw it the other way, and when you sum the forces correctly, including the direction you drew it, you would just get F of A is negative, which means it's opposite to the way you drew it. So the final joint you can draw it in the right direction. All right. So let's start with, again, the reason I usually start, at least in this joint, I will summation of forces in the y is 0 is because F of AH doesn't participate in that because it's in the x direction. So in the vertical direction, the only unknown component will be from F of AC. So I can solve for F of AC directly. If I start with summation of forces in the horizontal direction, I'll have both F of AH and the component of F of AC, so I'll have two unknowns. I would prefer to just solve it directly rather than write two equations and solve both of them simultaneously. So I say summation of forces in y is 0, F of AC multiplied by, and this is where you have to be careful, so the vertical component, horizontal component, I take cosine. In this case, I want the vertical component that's balanced in 6.7, so it's going to be a sine of theta. Equals 6.7. So 6.7 divided by 0.707, which is the sine of 45, and that gives me, for F of AC, 9.5 kips. And it's in compression. Let's see here. You can see it's compression because it's pushing out on the joint. We talked last time about this. Pulling on the joint's tension, it's pushing out on the joint, and it'll be pushing out on both joints at both ends of the same number. Force is constant. So that's F of AC. And then we have summation of forces. The x is 0. And I can solve for F of AH. F of AH. Not plus. So F of AH is to the right. The other two forces in the x direction will be to the left. So that equals 50 plus, so there's the 50 plus the horizontal component of F of AC, and you get that by, so we know this is 9.5 now. So I can just say plus 9.5 multiplied by cosine. Theta is the same, 45 degrees. So you add those together and you get 56.7 kips. And that's tension. So I'm going to redraw the joint here so you can look at it. We have 50, 6.7, 56.7, and 9.5. Okay, so you can look at it, and without doing any calculations, just take a glance to make sure it looks balanced before you move on to the next joint. So vertically, you can see 6.7 up, a vertical 0.707 and 9.5 looks about like 6 or 7. So that vertically, you can see it's balanced, right? Horizontally, we have 50 this way plus a little bit, 6 or 7 from 9.5. So that's 56, 57, and then to the right is 57. So 56.7. So you can see just looking, glancing at it, it's balanced without any. You've already done your calculations. This is just a quick glance. Okay. it'll be very obvious if this was reversed, for example, drawn to the left, you would see, oh, I've got an error, okay? The statics error. It's gotta be balanced. Is that clear? Yeah. And then the last step you do before you move on is you draw all those forces here, the ones that you just found. Otherwise, it's not obvious where we're going next. So if we try to start at joint C or H, let's say we wanted, before we did A, let's say we tried to go to H. There are 1, 2, 3, 4 unknown forces, right? And we have at that joint only 2 equations. So we wouldn't get a solve for those forces. They'd all be unknowns. If I try to start with joint 3, look at that. 1, 2, 3 unknown forces, 2 equations. It doesn't work. So instead, we started here because we had 2 unknowns. We could have started just as well at B. But that's it. Those are our choices. We could have started at B or at A in order to move forward. So now, let's draw. We have 56.7 shown like this. I'm going to show 2 arrows. And then the other force is 9.5 here. I'm going to show arrows going out. That indicates the compression, okay? So if I'm drawing the arrows like I mentioned last time, I don't also put plus and minus for these guys. I just give them as positive numbers. The arrows tell me if it's compression or tension. So now I can see that I can go to joint C next, not H, because H I still have 3 unknowns. I had 4 before, but there's still 3 unknowns, right? But at C we have 2 unknowns, so I can solve everything in C. So let's say next joint C. Draw everything. Here's joint C. In this case, there's an external load. You need to include that. So it's 50. Right? And I have the 9.5 coming up like this. That's compression, so it's pushing out on the joint, away, not pushing out, compression. And then I have F of CD. And look which direction I'm drawing it. The left, right? I could draw it to the right, but it's pretty clear. That part's gonna be the left. It's gonna balance the 50 and the 9.5. And I have F of CH like this. And that's gonna be down because it's gotta balance the upward force of that 9.5 kips. We also have to, one more thing I have to add to the sketch. So at each joint where you have the members coming in, which you normally do at an angle, you need to indicate where the angle is. So in this case, it's here. And like I said before, just by coincidence, because it's 45 degrees, cosine and sine are the same value, 0.707. If it's 60 degrees or 70 degrees or 30 degrees, 35, they won't be. And then you definitely have to use the proper cosine and sine to get the right results. And on top of that, you have to say, is the angle here or here? Because if you put the angle here, what you write as cosine would be sine, and what you write as sine would be cosine. So you have to be careful. So not just in your equations, like here where I'm writing sine and cosine, but then that has to be reflected, that angle, the correct location of that angle has to be shown on your drawing of the joint. Otherwise, what are you referring to, right? Otherwise, it doesn't make sense. Because there's nothing wrong with switching. You could, here I could write the angle as theta here and then write my equations associated with it. That's fine, but it has to be self-consistent. Okay. Plus your results. So summation of forces in the y is 0. I have F of CH equals, so that's down, that's going to be tension force, equals 9.5 multiplied by, the cosine would be the horizontal, so the sine is the vertical, sine of theta. So that gives me back the 6.7 kips. That's intention. 56.7. And if you actually, these are vectors, and I'm just sketching them not necessarily accurately, but the length here, the vertical length, and that length are identical, right? Because they're vectors. So this is a longer, a vector has, as we'll talk about maybe later today, but it has direction and magnitude. So the magnitude is represented by the length of the vector drawn. And so this, the vertical component of the 9.5 is the 9.5 sine theta. So vertically, this is 6.7. So when you sketch it, this and this are identical heights on the sketch. And then likewise, f of CD, the length would be equal to this length of vector plus the horizontal component plus that length there. In terms of visually what we're talking about. Okay, and then we have summation of forces in the x is 0. So we have f of CD is in compression. We have f of CD equals 50 plus 9.5 times the cosine of theta. $56.7. Compression. Let's redraw the joint here. I have 50. $6.7, a little bit longer back there. 6.7 and 9.5. So I encourage you all to redraw like this, each joint. And then the last thing is we'll transfer it over to the big font. So again, looking at it, you can see vertically it's balanced. The vertical component 9.5 is 6 equals to 6.7. Longitudinally 50 plus 6.7 of the, which is the horizontal component of 9.5. That's the compression force there, this balance. Is that clear? So let's transfer that. 56.7, that's compression, so it's pushing, force is constant between D, it's pushing to the left at joint C and pushing to the right at D, the member's in compression, so it's just pushing out. And then this is in tension. So what joint do we go to next? Yeah, H. 2 unknowns in H, 3 unknowns in B, 1, 2, 4 unknowns in I. So H, so it's the method of telling us where to go next. My joint, I have 56.7 pulling to the left, 6.7 up, pulling up, this is tension force. I have, I'm going to assume this is a tension force here, H to I, F of H I. And then I have this force here, which is F of H something, F of HD. And so like I said, if you sketch them the wrong way, it's okay, it'll work out. But in this case, it's pretty clear to me, just looking at it direction the forces will go. And I have to indicate where theta is, which is here. Okay, no vertical loads applied at the joint. So that's at H. When we get to I, we have 10 kips down, so we'll have to include that. Summation forces in the Y is 0. F of HD multiplied by the sine of theta equals 6.7 up there for it to be balanced. So F of HD is 9.5 kips, and that's in compression. That's this force down. Summation of forces in the X is 0. I have F of HI. So that's to the right equals 56.7 plus this F of HD, which now we know is a compression force of 9.5, so plus 9.5 times the cosine. I indicated where theta is, what location it is. So F of HI, 63.4 kips, 63,400 pounds. Let's redraw it here. 56.7 to the left, 63.4 to the right, 6.7 up, and this force down here at an angle of 9.5. Again, quick look at it, 56 plus about 5 or 6, so that's balanced by that to the right. Vertically, I can see the vertical component 9.5 is balanced by that. So looks reasonable. We'll transfer this information over here. 63.4 from H side. So this is tension here. Right? And then this is compression 9.5. So like I said, we're not going to solve the whole truss. It will take the whole class time today. But we'll get past E. I want to get past the halfway point. And you will have seen all the different little complications, including a joint like E that has 1, 2, 3, 4, 5 different members connected to it. Okay, so that was H. What's next? D, right? I has still 1, 2, 3 unknowns. So we have, this is no longer, it had 4 before, but now after solving H, it reduced to 3 unknown forces. When I go to D, originally I had 1, 2, 3, 4. When we solve for C, the amount of unknowns at D reduced to 3, and then when we solve for H, it reduced down to 2 unknown forces. So we have 2 known forces and 2 unknowns, 2 equations we can solve for, right? So that's when we say a truss is statically determinate, this is what we're talking about. That from statics by itself, we can go from joint to joint and solve for all the member forces. There are no unknown forces. We have great confidence that these results are right based directly on statics. So let's go to joint B. Next. At D, we have 56.7 pushing to the right from that member force, 9.5 coming up from both of those are compression members, right? Compression forces. And then down we have F of DI, and then to the left, the unknown is F of summing forces of a y is 0, F of DI, and if I happen to have an external force applied to the top of the joint, we would include that in this part of the equation. So F of DI is just 9.5 multiplied by the sine of theta. That's 6.7 in kips and tension. Summing forces in the X is 0. F of DE equals 56.7 plus 9.5 and the cosine of theta. That's 63.4 compression. So I can see horizontally, it looks like it adds up. We have a force down of 6.7 here. That's an up, 6.7, so that member's in tension. And then 63.4. Compression. Pushing out on both joints. So we've been diligent about, transferring the forces after each joint to this. Otherwise, if we forget to do it, then it would be confusing and a mess. So we still have two more that we want to do, 2 or 3. Next, we actually go to I now. Even though I initially had 1, 2, 3, 4 unknown forces, we now have 2 less. So we have 2 unknown forces. Let's put I next. Joint I, let's take a look. We have the force from the tension member here, pulling to the left is 63.4. Force up, tension member from I to D, 6.7. We have an applied force for joint I down 10, so we're including that. And then we have the 2 unknown forces, F of IJ to the right, and F of IE up. Summing forces vertically, we have, you have to be a little careful, the 6.7 is up, and the F of of IE, vertical component will be up too. So you have F of IE multiplied by the sine of theta. This is the unknown I'm solving for, so that's the vertical component of that, plus 6.7. In the same direction equals the 10 going the other way, right? 6.7 up, plus the way I've drawn this, I take the vertical component with the sine, and then that has, so we can solve for F of IE. That's going to be 10 minus 6.7 divided by the sine of that. You get 4.7 kips. These are all in kips. Tension. Then some forces in the x is 0. I have F of ij. That's to the right, plus the horizontal component at 4.7. So it's plus 4.7. There's the cosine of theta. Equals 63.4. From this I get F of ij is 60.1 kips, and that's in tension. You draw the joint 63.4 to the left, 60.1 to the right, 6.7 up, 10 down, that's applied for external force, and 4.7 applied force. Not that demand. Take a quick look. 60 plus 3. That's good. That's balanced by that 63. 6.7 up, 10 down, but there's also a 3 from about 3 from the vertical component, 4.7. So that balances up. So everything's good. I to J is 60.1. So this is this tension force here. That. And then we have 6.7 we already knew. What we didn't know was the 4.7 here. So this is tension.
Why is FIJ 60.4?
4.7.
I know, you subtract 4.7. Dude, isn't that like 59 point something? Hold on. Are you plugging the wavelet thing?
Okay, so we're not going to go to E next because we still have 3 unknowns. But we can go to J. So we'll do J and then E, and then we'll move on to some other notes. It's one kind of large example, so you can see how you do this joint. J is pretty clear. I won't even write it down. Summation of forces longitudinally. This unknown force is going to just be 60.1, right? It's going to be balanced by that. Summing forces vertically, that 10 will put tension in this 10. So that's joint J. Okay? Everything is just straight. Summing forces, this unknown force JK has to be 60.1, so you can do this unknown. And then summing vertically, that this force after the JE has to be. Now notice when you look at, if you don't look at the bottom, if you just look at this, you have no idea what this force F of EJ is, but it's the same as F of JE, right? So when you look at this joint, it's very clear this has to be a tension force of 10 kips. If you look at the other end of the same member, it's not obvious. You got all these members connected, okay? So yeah, but the force stays the same with the whole length. And then joint E is the last thing, and then now we have the 2 unknowns here. So the last thing is joint E, in this example. have 63.4, 4.7, 10, F of the F, and F of EK. This is theta. And this is so let's start with summation of forces in y of 0. I have F of EK multiplied by sine of theta plus 4.7 multiplied by sine of theta. So this is going down, right? Plus 10 is 0. So we get a negative. F of EK, and I take all that to the other side and divide by sine, I have a negative, which is minus 18.8. Okay. So therefore opposite direction to draw. Okay, so that's instead of that way, it's actually like this. 18.8. A little circle. So when I redraw it, also when I sum the other forces, I need to. So I have summation of forces in the x is 0. The only other unknown is F of the F. So now I have F of the F, which is this way, plus 4.7 times the cosine of theta. So this plus the horizontal component of this equals, oh no, plus, see the way the 18 is? So it's plus 18.8 times the cosine of theta equals 63.4. And technically I could have done it the other way and then called it just F of, when I solved for F of the, called this F of the EK. I could have said F of the F plus this, and then I could have said equals 63.4 this way plus F, the unknown F of EK cosine of theta. But then when I put in F of EK, I have to be really careful. I have to put in, if I wrote that as F of EK, I have to put in minus 18. So doing it the way I'm doing it, by switching it here, now I'm drawing it the right way, right? So F of the F is to the left, plus 4.7 cosine theta, that's to the left, plus, so the 18.8 is this way, 18.8 times cosine theta is to the left, that equals 63.4 to the right. So, by recognizing that I drew it the opposite direction to the actual direction, this helps. And so it's actually not a tension force, but a compression force. So I end up with 46.8. Kips in compression. So redrawing the joint, especially important in this case because I'm looking at the direction. 63.4, 46.8, 10, 4.7, and 18.8. And this is joint. Center transfer. Let's take a quick look, make sure it looks reasonable. So I've got about 3 this way, 40 this way, another 10 or 15, 46, 56, and 60. That looks balanced horizontally, vertically. I have now this 18.8 is going in that direction, some compression. So the vertical component is about, let's say, 13 to 14. And then I have 10 down and about 3, the vertical component of this down, so that balance is vertical. So it looks reasonable. We'll transfer that. 46.8 compression force here. And 18.8. Okay, I'll take a 10-minute break. Okay. Talk about method of sections. It also gives you member forces for a statically determined truss, like Becky's joint stuff. Completely different method, but since it's based on overall statics, you're getting identical results. It has different applications. Method of joints is when, as we saw in the prior example, when you want to solve for all of the member forces, every one of them, in your structure. Method of sections is, let's say you just want to solve for 2 or 3. Right? Way out in the middle of a truss. We don't want to take 5 hours to get there to solve for everything. Method of sections allows you to do that. We can just apply the loads on the truss, solve for the reactions like we did before, and then just take a cut, an imaginary cut somewhere out in the middle of the structure, right through the structure. And every member that we cut through is a member we can solve for the forces directly by taking the section cut. So let's talk about how it works. And we'll do some examples. So we're going to pass an imaginary cutting plane right through the structure, all the way through. But you have to, and this is important, you have to cut through the members that you want to solve for the forces. You can't cut through the structure and then not have cut through the member that you're trying to solve the force for. You won't get that result. Three equations of statics. So this says plane must pass through the members of interest or the members where the forces are found, and 3 equations of statics. So when we did method of joints, we used 3 equations overall for the reactions, just like we will here. Okay? 3 equations overall to solve for the reactions. But when we went from joint to joint, we only had 2 equations. But when we take a section cut, we have 3 full equations. We have summation of forces in the x of 0, summation of forces in the y, and summation of moments about a point. So we can add that third one, which means that we can solve for when we take a cut, we can cut through 3 members. 3 members, so we can solve for all 3 because we have 3 equations. Right? So let's look at an example. example. We're going to have different forces. We said C here, we're going to have the force down 60 kilos. Otherwise, the geometry of this truss looks like this. We're spacing 10 feet this way. The roller support here. We're going to do is, we'll just take 4 section cuts, but just be aware when I'm just doing this to demonstrate how the method works, that you are the ones that are going to have to decide where the section cuts are taken. So like section 1-1 will be just to the right, a differential distance to B and I. So right here, see that? 1, 1. That's section 1-1. Now, so on an exam or a homework problem, I'm not going to give you the section cut. You're going to have to figure out where to take the section cut. Okay? In this case, if you were looking for, let's say, force IJ, force IC, or force BC, see how it's cutting through those 3. So you can solve for those 3 by a section cut like that. So if the question was, what's the force in member IC? You could take this section cut and solve for it. That's all sure. Or if the question was, what's force of a BC? This would work, or I. So that's so let's keep that in mind. Section 2-2 is just to the right of J and E. And then look at the members that I'm cutting through. Those from that section, and these section cuts don't depend on each other. So I'm not doing them in any order. They're just different examples of section cuts. These ones happen to be diagonal. They're not all diagonal. You can do vertical cuts through too. You don't want to cut through. You don't want to cut such that you cut through more than 3 members because you won't be able to solve any of them. Right? As long as you cut through 3 members, you have 3 equations, 3 unknowns. You can always solve for it. That's section 1-1, 2-2. 3-3 is different. It's diagonal, but instead of to the right, it's to the left of K and M. It's right here. This is 3-3. And then I want, those are all diagonals, so I want to show a vertical cut. Let's do a vertical cut just to the right of I and C. Like this. Then let's solve for the reactions. This is 0. I sum moments about right. I get 40 kips here. And summing forces vertically at this point. (20 + 40 = 60). This 60 kips is not placed in the center, it's off center. So that's why there's larger reaction to the left. Okay, so those reactions are solved in the normal way. And then now let's we'll look at each of these 4 section cuts separately. So we'll start with section 1. So the way it works is you show the structure all the way up to the section cut. And recognize that the section cut is just a differential distance past the two joints. It's not an actual distance, it's a dx distance past. Okay? And that's important because when you write the dimensions, you need to show dimensions up to the joints. So, for example, let's do section 1. So we're going to show the structure up to that section cut, and then we'll put the dimensions on it too, so that because you need, it's helpful to have those dimensions on each separate section cut drawing, because you're going to be summing not just forces but moments about places. So it looks like this, right? And then it goes like this. So this is for section 1-1. We have this boundary here, and this is 0 in this case. If it had a force there, we would include it, and then the force up is 40. And let's also label it. This is A, so we know where we are on the overall picture of the truss. H and I. I'm going to erase this so I can put the dimensions on. 10, 10. It's easy to make mistakes if you don't show the dimensions. Okay, and then I have f of ij, this, f of ic, and f of bc. So we've cut through the three members. So we've cut right through the structure, right? And these forces here represent, those are the ones that were actually cut through, right, for section 1-1. So there's f of ij, f of ic, and f of bc. We didn't cut through any other members. So those forces here, those three forces, represent the behavior of the rest of the structure. So you don't need to include the rest of the structure for the statics tool, right? But on the left, you have to show the whole structure, including any applied forces and reactions as indicated there. Okay? So we have, now this is interesting. Let's do this first. Summation of forces and the y is 0. So we're not just summing these forces at a section, we're summing it for this whole picture, okay? Statics as a whole. So we can see right away, look at this. What's f of ic? What's that equal? It's got to be 40, right? That's 40. Summing forces first. So it's 40 kips, and it's in tension. This is 40. That was it. That's the whole, I mean, that's a simple calculation, right? Now, if we solve for that, if I asked you to solve for that same thing, f of ic, for this problem, and you didn't know method of sections, you did it by method of joints, it'd take quite a bit of work to get out there, right? You would start from here, and then you would go to here, and then to here, and then to there. So it'd take you 20, 25 minutes to get out there, method of sections. In fact, there are no calculations even required, right? You cut it, you redraw the structure, and you can see by statics there's no other force in this picture than this 40 down. So it has to balance the 40 out there. Yeah?
How did we get 20? Were those just given?
Oh, those are reactions.
Yeah.
I'm just saying you solve for them. You've already.
They're already solved for.
What?
They're already solved for in the situation.
I mean, I just assume that we know how to solve for them. So you would just take moments about G and solve. That's 40. 60 times 10, 20, 30, 40 equals this reaction times 60. You solve for it, you get 40. Sum the forces, then you get the other one. 20 plus 40 is 60. So yeah, I just gave you. Okay, so now let's say, and you didn't need to solve for f of ic first, let's say sometimes you do depending on the section and the situation. Now let's say I wanted to solve for f of bc. I would just take moments about I, right? And I wouldn't even need to solve for C first. So let's say a summation of moments about I equals 0. So again, we're in a position of everything clockwise equals everything counterclockwise. I'll start with the clockwise, counterclockwise, because that's the f of BC is the unknown I'm solving for. So I have f of BC multiplied by 10 as counterclockwise moment equals the only clockwise moment is this 40 times the distance over to I, the horizontal distance, or the not perpendicular distance, which is 20. 40 times 20. So even this doesn't really require much calculation, right? 20 over 10 is 2 times 40 is 8. So therefore f of BC is 80 kips, and you can see its intention. Then the last equation available to us, statics, for this is summation of forces if the x is 0. Now there's no force here, but if there were longitudinally, then we would have to include that. You're including the whole picture up to that section cut, the whole structure. In this case, we have f of ij just equals f of bc, but in the opposite direction, right? 80 kips. Opposite, we have to sum. And that's, this is in compression. That's this 80. So we have a compression force of 80, tension force of 80, and tension force of all three, without having to start at point A and move through the structure. Is that clear? That's one example. Section one. Go through the others. Let's look at section 2.2. So it's also just to the right of joints, in this case joints J and E. Ten here. Let's label these A, B, C, E, H. It helps to label the joints in section cuts like this, otherwise you don't really know where you are, you get lost. Okay. Like that. We also have to be careful at C, we have a force, we're far enough over where we have a force applied, we need to include that because it's here, right? So we're including everything up to J. We have F of EK here. Unknown force that we cut through, F of JK. And F of EF. So we're going just a differential distance past J, E. So we're cutting through JK. So there's a compression force indicated there. cutting through the vertical member EK, so that's F of EK there, and the horizontal member F of EK. And then again, those three forces here represent the balance of the forces for the remainder of the structure. So it's static. So we'll start with a summation of this is section 2. Start with summation of forces in the Y. That'll allow us to solve for F of BK. F of BK. So you have to be careful, right? Because there's a 60 also. So it's not just the reaction like last cut. We're including summing the forces doing the statics on this whole truss up to the cut from the left. So we have 40, but we also have 60. So you have to say F of EK plus 40, right? Equals 60. This plus this equals 60. So we get F of EK. 60 minus 40, that's 20 kilos. So again, simple calculation, but you still have to make sure you include everything correctly. That's tension based on the direction. So this is 20. Now we can solve, let's say, and we didn't have to, we could have done this first. We could solve for F of JK. The reason I say we could have done that first before F of EK is we're going to sum moments about E, right? And F of EK and F of EF aren't needed for that because they go right through that point. So we have summation of, let's say, moments about E equals 0. And the force I'm solving for that I'm interested in, the reason I'm taking moments about that point is F of JK. So I have F of JK multiplied by the height, 10, equal distance. That's a counterclockwise moment. So is the 60 producing a counterclockwise moment, right? So it's plus 60 multiplied by the distance to E, which is 20. That equals the clockwise moment of this reaction at 40 times 10 to the 40. So I get 40 gives. That's compression. Summation of forces in the X is 0. I have F of the F must be equal to 40 kips. In tension. And that's just balancing that 40. There are no other longitudinal forces. If there were, I would have to Section 3.3 is a little different, so that's it for section 2.2. That's all three of the unknown member forces. Section 3.3, we took the cut just to the left instead of to the right of the points, just to the left of K and F. So we're going to, in that case, we're drawing a structure that's on the right up to that. Okay? So this will be section 3.3 here. Include the reaction on that side, G, which is 20. we cut 3, we're going just to the left of K and F. And so we're cutting through KJ. That's why there's an unknown force F of KJ. We're cutting through KE. So there's the force F of KE, the vertical force. And we're cutting through F of, remember, EF. So we have an F, E or EF. So we can start with summation of forces in the Y is 0. And I have F of KE equals 20. Right? Simple as that. There's nothing else there. So again, method of joints, you would have to go from joint to joint to get out there, and here one simple cut, you can see what the force is visually. Not any real time. Let's sum moments about K. In order to solve for F of FD. And F of FD, this is a clockwise moment multiplied by 10. Equals, the only other moment contribution is from the reaction, it's a clockwise moment. Sorry, the F of FD times 10 is clockwise, that equals the counterclockwise moment of 20 kips times the horizontal distance of 20. So 20 over 10 times 20, this is 40 kips. And that's tension. And then summing forces in the x direction. You can see, again, there's no horizontal load here. There can't be, it's a roller. And there are no horizontal loads applied within this part of the truss or anywhere actually. So we get F of KJ must also be equal to 40, but in the opposite direction. That's compression. And the F of KE is 20. This is tension. That's sections 1, 2, and 3. Section 4, we'll do that as the last thing. It's just to the right of I and C.
Imagine just getting hammered after I run a fucking half marathon. My roommates and friends.
I'm too anti-social.
Bruh.
Good.
So I know we're just about out of time, but let's just finish this. Section 4.4 is just to the right of C and I. So then you need, because of that, it's a differential distance. Even though it's a differential distance, you have to therefore include the 60 kips. So that's important. So we have F of IJ, F of CD, and F of CJ. So summation of forces in the y is 0. We have, we'll solve for f of Cj, but it's at an angle. Remember we cut through, right? So we have to take the component of it. And we have to include the 60. So we have f of Cj multiplied by the sine of theta plus 40 equals 60. So f of Cj equals 28.3 gives intention. Then we'll sum moments about C. Solve for f of ij. F of ij multiplied by 10. The 60 is going through there, these forces are going through there, so it's just this 40 equals 40 multiplied by 20. F of ij is 80 gives compression. And then, so now you have to be careful when you sum forces in the x, because there are two forces there. So we have summation of forces in x is 0. F of CD is what I'm looking for, is the third. Remember, so it's F of CD plus this 28.3, that same direction, times the cosine of theta, equals 80. So we needed to include the horizontal component. We're including all the horizontal forces. So it's F of CD plus that horizontal component at 28.3 must equal 80. And then we get F of CD is equal to 60 tension. Tension. So that's it in a nutshell. We'll look at one more example next time with method of sections and then go on to something else. I'll post the homework later today, and I'll also include the due date, such that you have some time to study the solutions that are